He's working. All right, I will begin with the word of prayer. Dear my Father, we thank you for this day. Again, Lord, I thank you for this opportunity we've had just to meet together and talk about algebraic topology this semester. I just pray that you help us to draw things to a close here as we talk about cohomology just for today, Lord. In your name I pray. Amen. So, of course, I would like to say, first of all, I read Rotman, and it's beautiful. Like, the start of his cohomology chapter is just it's just beautiful. It's breathtaking. It's just wonderful algebra. I mean, what he has at the start of this chapter, I should mention at least. Where is it? Like in the space of 4 or 5 pages, right? He defines pretty nicely, you know, what's an A module, right? You know, how to describe an exterior power of an A module, you know, the definition of the Durham cohomology over Rm, you know, a little discussion of exterior differentiation in R3, how it relates to curl and divergence, cool stuff, generalized Stokes theorem, and then, you know, it's all very pretty. And he even, you know, the next thing here he has his cohomology group section. He shows that given, you know, one of these, what's it called here? SPXG. So the homomorphisms from singular P chains to an abelian group G gives you a particular sequence, and he talks about how it's actually homology with kind of a wrong labeling, and then he introduces the, you know, the usual notation with the upper index rather than the lower index for the cohomology, and, you know, introduces n cochains and n cocycles and the nth cohomology group, all that. It's very pretty, but I think I'm going to go a different way and look at Jeffrey Lee's book here today, because I think we'll get a little bit further and a little bit more explicitly than following Rotman, which is, of course, as usual, beautiful, but a little short on examples, I think. So here I am using, this is, of course, manifolds and differential geometry. You may recall that when I got stuck on the detail in Rentland, I may have, you know, I remember I pulled this out of the thin air and started lecturing from here, annoyingly, for like 2 classes in advanced, because of the combinatorics and the wedge product were a little bit sketchy in Rentland. Actually, they weren't there. But it's, you know, there are many gory details in this book, and by the way, there's a complementary online supplement with like solutions or something that's about the same length. I haven't looked at that, but I wonder what's there. There might be rather explicit calculations of cohomology in there for all I know. I should really look at it. All right, so let's start at the start of his chapter. I'll try to get through it as fast as I can. And so here it is. So mostly we're focused on the Durham the Durham cohomology. That's what this chapter 10 in Lee's book is. And here it is. So for a given n manifold M, we have the sequence of maps called the Durham complex. So what's that look like? So we've got 0, and then exterior derivative, d. 0 forms over m. And exterior derivative again, 1 forms over m. And so forth, until you get to n forms over m, and then you got 0. So this sequence of maps is called the Durham complex, and we can define Durham cohomology groups by quotients of the following. Okay, kind of the usual thing. Let me get to it. So the Durham cohomology groups, HK of M, excuse me, it's a quotient of Z upper K of M mod B upper K of M. All right, where the cycles, ZKM, are what? Those are the kernel of what? Of the exterior derivative mapping from where? From omega km to omega k plus 1, right? So in other words, the k-forms, right, whose exterior derivative is 0. Of course, included among those would be the exact forms. So BKM is what? It's the image of D, which is mapping from the k minus 1 forms over M to the k forms of M, right? So again, those are the closed forms, those are the exact forms in our usual language, right? Back is screwy today. I don't know what's wrong with me. Hoping by walking around for a while I would like fix it, but all right. So again, these are closed. These are the exact forms, right? So non-trivial cohomology groups come from what? The existence of closed forms which are not exact, right? The quintessential example of this, of course, is in the plane, and he gives that example in here. We'll keep going here. I guess before I get to that, just a little bit more sort of blast from the past here, I suppose. Those are closed k-forms, or k cocycles. Those are exact k-forms, or k coboundaries. I guess I should say these are also the coboundaries. These are the cocycles. Let's see here. If you have a mapping, a smooth map from a manifold M to a manifold N, right, what else can we do? Remember what we can do with a smooth map with differential forms?
Pull back and push forward?
Exactly. We can pull back. So he says if we have a cohomology class beta, so we use brackets to talk about the cohomology classes, right? The set of cohomologist k-forms. So if that's a cohomology class over N, then the pullback of that is a corresponding cohomology class of M, right? So we can pull back forms, we can pull back classes of forms as well. And he says that the pullback, he says that this depends only on the equivalence class of beta, right? So here's an identity. You write it down here. If we have beta minus beta prime equal to the differential of eta, right? Then pull back beta minus the pullback of beta prime is, of course, the pullback of d eta, right? But remember, pullbacks commutes with exterior derivatives, so this is the differential of the pullback of eta. And thus we may define, well, basically he's leading up to the definition. Thus we have a f star, a mapping from k forms on N to k forms on M. How do you do it? F star of the cohomology class of beta is equal to the pullback, the cohomology class of the pullback. Why is that map well defined? I mean, what is brackets beta actually explicitly? It's an additive coset, right? It's beta plus bkn, right?
And then we just kind of showed.
Yeah, I mean that's what we've shown. I was just begging the question, but yeah. So exactly, if we took two different representatives, beta prime would be equal. I mean, well, beta would be equal to beta prime plus d eta. Those are two different representatives of the same. Beta and beta prime are different representatives of the same cohomology class. And this calculation right here shows you that they both map to a coboundary, as it's known, I suppose. Consequently, that map is well defined. Yeah. All right, so, and the next thing he does, which I think is important, it's definitely worth a minute of our time, is to consider the one form. Look at M equal to the plane without the origin, right? And you can define this guy, theta, x dy minus x dx, y dx rather, over x squared plus y squared, right? That's defined on the deleted plane. And he says we got this one form by taking the exterior derivative. I mean, this is basically the exterior derivative of the inverse tangent function. Right. Now, of course, that doesn't make sense. I mean, inverse tangent y over x doesn't make sense when x is equal to 0. But if you take the derivative of that, the exterior derivative of that, forget about where it came from, right? And just look at this form. Well, that form is good on the deleted plane, even though the thing that we were exterior differentiating to get it wasn't defined on the whole y-axis, right? Anyway, so he says one can extend theta to be defined on the whole plane minus the ray x less than or equal to 0, y. He says you can define theta like this. Inverse tangent y over x, that's good for what? X greater than 0, right? You can do inverse cosine of x over, don't tell my Calc 3 students about this, this is a formula that they want to know. Inverse cosine of, I make them think about it, I don't give them this formula. I could give them this formula, right? I never say this formula in class. Because if I ever wrote it down, they would all, like so many robots, try to use this formula every time we asked a question about standard angle. I'm deliberately vague about standard angles when I talk about them in class. Because I want them to think through it for themselves. I don't want to give them this formula. But here's a formula.
Wait, isn't that the derivative of sine inverse?
What's that?
X over... No, I'm thinking of x over x squared plus 1.
Oh, this is like, look at this. I usually think about it in terms of shifting the tangent, but this one's just formulas in terms of inverse cosine minus inverse cosine. So this is if x is less than or equal to 0 and y is less than 0. So you see what's missing is what?
Both zeros. I guess y equals 0.
Yeah, y equals 0, x less than 0. So this is the standard angle function on the slit complex plane, right? Or the, missing the negative real axis basically is it. So theta is defined elsewhere. All right. So anyway, one may check that, so you can, I shouldn't use theta, I may use something else for this. It looks different. He uses a funny looking theta in the book. Let me use something genuinely different like this thing there. So you can check that D, why didn't I use a letter I can draw? This thing is equal to
4 o'clock p.m. p.m.
You can show that that's equal to 0 on the deleted plane, right? So this is an example of, this is what then? So what is it? It's got their derivative. So what is it? It's a cocycle, right? Right.
Yeah.
And it's, but this is not a coboundary. You can't write, here, right, there does not exist, let's say beta, such that d beta equals, no. If there was such a thing, that would give you a globally defined angle function, which just isn't possible. There has to be a discontinuity. I mean, it's possible, right, but there has to be a jump discontinuity, in which case you certainly can't exterior differentiate it at such a point, well, such a rate. So, as he says, you have a smooth one form on the deleted plane, its exterior derivative is 0, there's no function that it gives it back to you as its exterior derivative. And from section 2.10 we know that for any ball in the deleted plane there's a function such that, he says locally anyway, at least you can write, there is a theorem that says that you can write this is the differential of some function locally at least on any epsilon ball away from the origin. So that's pretty, right? If I pick any point like here, right, I can express as equal to, this restricted to this ball as df for some choice of function, some f there. Just I can't do it on a neighborhood of the origin. Let's see here. He says assertion 3 means we could say that nu is what we might call locally exact or locally conservative. What prevents us from finding a global function? Right. Could the same kind of situation occur if the manifold is R2? He says nope, the difference is between R2 and R2 without the origin is that the first cohomology group of R2 is 0, where the first cohomology group of R2 without the origin is non-zero. I mean, this proves it's non-zero. It's kind of just, this is tautology 101, right? I mean, exercise 10.1, verify 1 and 3 above. Okay, anyway, yeah, whatever. Let's see here. He ties this to the discussion of exact differential equations, right? Like, this is very much tied to the problem of finding solutions to exact differential equations as well. All right, anyway, since we have found a closed one form on the deleted plane that's not exact, we know that the first cohomology group is non-zero, but we're not yet in a position to determine this first cohomology group completely. He says we'll start out with even simpler spaces and eventually develop the machinery to bootstrap our way up to more complicated situations. So, we get here. So you might guess, so the next discussion, 1 point space, right? M equal to a single point. Kind of dumb. And so if M is a single point and hence is a zero-dimensional manifold, in this case, we have that the K forms. I'm sorry, every time I write something like this, I just feel like so dumb to even write it. I don't know, but whatever. I guess that's why I'm not a good mathematician. ZK of T. So what is it? You have the reals for K equal to 0, right? And you have 0 for K greater than 0. Why is that? Oh. I mean, It's a little bit of an abuse, right? I mean, technically you have constant functions for k equal to 0. But there's an obvious correspondence between constant functions and the reals. And that correspondence we're using. And obviously, you can't do anything but a constant function from a single point space. You can't define a one form on a single point space. Not as I understand one forms anyway. And how about the boundaries? Well, the boundaries are all 0, right? So boundaries are all 0. In other words, in short, this is HK of, right? Because the boundaries are trivial. So the cohomology is just the reals of k equals 0 and it's 0 otherwise. Alright. Next case. So that was, I guess that was the 0th case, I'll call it 0. Case number 1, m equal to the reals. Alright, so how's that go? Here, again, z0 is clearly just constant functions, it's isomorphic to r. On the other hand, the boundary, b0 of r is also equal to 0, and so he says h0 of r is also equal to r. Let me just pause to think through that for just a second here. Does that make sense to you guys? If we take the manifold to be the reals, if we're looking at functions, right, 0 forms are functions. Functions of the reals whose exterior derivative is everywhere 0. Those would be cycles. What does it mean if the exterior derivative is everywhere 0?
Constant.
It's a constant function. Can you obtain a function as the exterior derivative of a -1 form? By definition, no. Okay, I mean essentially you can't do that. So there are no boundaries. So that's this. All right. Moving along. Now the exterior derivative goes from. Let's see here. All right, so he's got a little bit more to say here. So what's he say here? He says we have D going from 1 forms over R to 2 forms over. I mean, there are no 2 forms over R. I mean, what? What's his point here? Well, he says this is equal to 0. Okay, I'll buy that. Right, dx wedge dx is 0. So z1. So what does he say here? He says we see that z1 of R is equal to, oh, that makes sense, doesn't it? Did you see that? So every 1 form exterior differentiates to 0. So every 1 form over the reals is exact. Right? Now if he says if come on. G of x dx is an element, suppose you got G of x dx is an element of omega 1r, right? Then he says, basically he's going to construct a potential function, f of x equals, can you guys tell me what it should be? I bet you can.
You're trying to find potential for g of x?
Yeah, what can I differentiate to get that? Integral, okay, of what? G of x. So I'm gonna trade you that g of x for g of t dt. Now he's got g of x dx, but I think that's bad form. So this, I think, yeah. And obviously the derivative of this is, exterior derivative of this is that. So, thus what? What's that show?
It's a boundary. Or a co-boundary.
I mean, so my question is to you, what kind of one form over the reals is this? What kind of one form is this? This is a,
It's not exact.
it's an arbitrary one form, right?
Oh, right, yeah.
And what did we just show?
But it's exact.
Right. So, in summary, come on, don't drop. Sorry, I gotta put a bookmark in here so when I come back I can find my spot. So the, sorry, I'm fighting with this cord. Let me fix it. I mean, so what we have here is kind of an interesting but uninteresting quotient, right? Interesting because there's actually something to divide. Uninteresting because it works out to 0. Come on, you stupid thing. Oh, yowzers. Tired. Keep rolling over this. See if we can make out of this meeting without pulling down my fluorescent lights. Here. We've made it a semester. We only got like a couple more hours to go, and we made it despite them being perched up there precariously the whole time. Just waiting to crash down and leave shards of the fluorescent light bulbs in all my books.
Mm-hmm.
Thus rendering my office uninhabitable. It's not gonna happen though. It's gonna be okay. Sorry. So anyway, in short, H1 of R is what? It's basically R over R, right? So it's because basically we just saw that, well, I mean that's up to isomorphism, but every, oh I guess that's not what I thought. Well, that's too much. That's not true. That's not true. That's not true at all. Right? Smooth functions is not the reals, is it? No. Sorry, must be hard to watch me today. Let's see here. So the point was that
It's like omega 1 of R for omega 1 of R.
right. And I think that it's clear that up to, basically up to multiplication by dx, omega 1 of R is just smooth functions, smooth real valued functions over R, right? So like omega 1 of R would be like C infinity R, you might call it, right? In this case. It's not that, but it's isomorphic to that, is what I'm trying to say. Is okay, so
It's kind of like our musical morphisms. They're actually isomorphisms.
yes. Good point. I feel like that whole discussion kind of fell flat. Let's see here, but sorry. It was awful. I regret it. All right. I'm currently resisting the urge to say something about Sharp, but I almost did. All right, so from this modest beginning, we'll be able to compute the Durham Cohomology for a rather large class of manifolds. Our first goal is to compute the kth cohomology group of Rn for all k. In order to accomplish this, we need some preparation. The methods are largely algebraic, so we need to introduce a bit of homological algebra. So at this point, he introduces a differential R complex. So R is a commutative ring. C is a direct sum of modules together with a linear map from C to C such that D squared is 0 and that the differential on K maps to the K plus, the subset of the K plus 1 space. You get this sequence of linear maps. Let's see here, I don't know how much of this I should write up on the board. I feel like we've written all these things before, but not exactly. So write them. Clean this silly place. So definition, R a commutative ring. Then differential R complex again is a direct sum of modules. Together with linear map D and decomposed with D 0 and also D sub k, which is going to be D restricted to CK, right, is a mapping from CK to CK plus 1, right? In other words, more to the point, D of CK is a subset of CK plus 1, right? And so what's a chain map, right? If you have two different, this is called a differential complex, all right? So suppose you got two of these guys, all right, A and B. And you can talk about chain maps between them. So if I've got A, K minus 1, AK, AK plus 1, BK minus 1, BK, BK plus 1. And of course we have, these are differential complexes. So what do we got? Well, he just uses D everywhere. Fine. I mean, I guess if we were in Rotman, we'd probably put a prime on one of these. And so here there's a map F sub K minus 1. Here's a map FK. Here's a map FK plus 1. So basically a map F from A to B, all right? Here, of course, A is the direct sum of the A sub k's, and B is the direct sum of the B sub k's, or whatever, right? These are chain complex. These are differential complexes. A map F from A to B is called a chain map if F is a degree 0 graded map such that D composed with F is equal to F composed with D. With all of the requisite indices deserved thereunto. He says, notice that if F goes from A to B as a chain map, then the kernel of F and the image of F are complexes. Right? And one problem with my printing is it changes equals to minus in some places. So like in my book it looks like this. MF, the image of F, is minus the direct sum of K. If you're really lost, this will really mess with you, you know? But of course this is, you know, I got this, this is an Eastern Economy edition, you know? I don't, you know, I'm but a poor math professor, you know? And so I don't have a budget for the fancy proper Springer versions of all my books, and
That's the equals.
yeah, that's an equals. Now they could afford the equals for the kernel, corresponding kernel comment in here. But the kernel of a chain map is also a complex. That's kind of cool. All right, he says, thus the notion of exact sequence of chain maps may be defined in the obvious way. So,
And this is pretty much what we did in chapter 4.
right, just now the maps are running the other way, right? Like we had the delta, or maybe we had the numbering.
Right.
Yeah, I think it
Right,
was
the other way.
numbering.
So, but it's, yes, it is very, very much chapter 4-ish. And so, of course, once you have all this, you can define the cohomology over C, right? And it's going to be what HKC will be kernel of D restricted to CK mod the image of D restricted to CK minus 1, right? I guess I'm supposed to have upper K minus 1. I'm sorry, my labels are upstairs, not downstairs on these components. So that defines the kth homology group of the differential complex C. Right. And he defines a short exact sequence. And he shows that there's a corresponding long exact sequence of cohomology groups. And let's see here. I don't think I'll write those things down since I think you guys are kind of well versed in that part already. You know, the proof is interesting, but you know, basically it's just what we've done before, except now instead of having this esoteric delta thing between either simplices or ends or singular simplices, we now have the exterior derivative. Well, or something that behaves like the exterior derivative on this abstract algebraic object, right? So up to some formal algebra, it's the exterior derivative. All right, so let us review the situation we have with Durham cohomology, noticing how it fits the abstract homological algebra above. We let omega k equal 0 for k less than 0, and we have a differential complex D, which is going from the exterior algebra to the exterior algebra, where D is the exterior derivative, and omega m is the direct sum of the k forms of different various degrees, right? In this case, the let's see here, how does he say this? He says, as a point of notation, we're going to, I'm going to erase, I think I don't need the chain stuff here for a while. So as a point of notation here, we'll just say that HK of M is actually the homology of the exterior algebra over M. The exterior algebra, right, is naturally a differential complex where, the k-forms are acted on by a exterior derivative in the natural way. So this is the Durham cohomology is the cohomology of the exterior algebra. Now, now he wants to talk about pullback a little bit. If we have a smooth map from M to N, we have that, so F from M to N smooth. Then we have F star, natural map from where to where, from the exterior algebra on M to the exterior algebra on M, right? And since the pullback commutes with the exterior differentiation and preserves the degree of differential forms, that means that F star is in fact a chain map. Thus, we have an induced map on the cohomology denoted by F upper star, so that F star is then naturally, like this, right? And in particular, he suffers from the same problem that Robin does. Look at this. Look at this. Look at this. I tell you, what's wrong? What's up with these people? It's so hard to. I just tell you, whatever.
More importantly, they're using the, well, I guess that could also be such that I'm used to that being type.
So are they violating your type rules as well, or is it
Yeah.
or is it good?
They're violating.
They're violent. Oh, I'm sorry. I'm so sorry. I guess they're just not your type. Let's see here. Nathan meets some girl in grad school. Stuart Lawyer Langer, they have a conversation. Nathan says, "I'm sorry, you're just not my type." Girl says, "What do you mean by that?" Nathan's like, "I don't know. Do you have 3 hours?" Let me explain to you in the technical sense why we can't be together. I like Justin Bieber, but you like Britney Spears. Just don't ever work. Nathan's like, that's fighting. Them's fighting words. You know, I'm a big Britney Spears fan. Are you a believer?
No.
Okay.
I'm neither a Justin Bieber or a Britney Spears fan.
That's good. Sorry. Okay, so that property of the pullback, right? This thing here. Well, the property of the pullback is then inherited by the chain map, right? That the pullback of a composite is the composite of the pullbacks in opposite order. This is part of why it is what?
Contravariant functor.
Indeedly doodly. It is a contravariant functor. So this chain map together with the assignment of the Durham Cohomology to M as a contravariant functor. All right. He's got a remark down here. I wonder what it's about. If alpha is a K form and beta is an L form, for any alpha prime in K, dang it. See, there's a space. It's my typesetting again. Look, see, it's very very annoying. I mean, I guess I'm making an advertisement for spending $100 on the book. This $20 version does have certain problems. Like here, I don't know. It's a K plus or minus 1 form. I'm not sure. Right?
Exercise left to the reader.
So, K plus. Don't forget to take your packet with you. Right. Where are we? Well, he adds d alpha prime to alpha. So if alpha is a K form, that means that alpha prime is a minus 1, K minus 1 form. Mystery solved. Okay, so alpha prime is a K minus 1 form over N. Oh, this is actually a very interesting comment. So what he's explaining now basically is the fact that not only is it it's this differential complex, right? There's also a way of multiplying things in the complex. It has what's called a graded ring structure, which again, Rotman defines beautifully at the start of that chapter. My goodness. Just so efficient. So let me just write that down actually. I think we're okay. So his point is, if you look at alpha plus d alpha prime, and you wedge it with beta, well, that's equal to alpha wedge beta plus d alpha prime wedge beta, right? But that is equal to, and here's a little chain rule for you. Well, actually, this is in some sense, this is integration by parts. Check this out, yo. This is d of alpha prime wedge beta, closed differential, minus 1 to the k minus 1, alpha prime wedge d beta. See, there's some sneaky stuff right there. But integration by parts. I mean, okay, it's the graded Leibniz rule. Anyway, the point is that this is equal to alpha wedge beta plus d alpha prime wedge beta. Why did I get rid of the other term? Oh, context, right? So here we're supposing that we've got alpha, K cycle over M, beta, a K cycle, an L cycle over M, all right? And alpha prime, an element of omega K minus 1. That's the context here, right? So if beta is an L cycle, that means that d beta is 0, right? And what's this calculation show you? He says similarly, likewise, if we take alpha wedge beta plus d beta prime, we can prove that that's equal to alpha wedge beta plus the differential of alpha wedge beta prime, right? So he says, so we can define a product. Here's the product. We take a cohomology class of alpha, wedge the cohomology class of beta, and shockingly we define it to be the cohomology class of omega wedge beta. He says this gives the Durham cohomology of M a graded ring structure. And in a nutshell, that's one of the reasons that cohomology is more interesting than homology, is because of this ring structure, right? Now, in my algebraic topology class, we defined this abstract thing called the cup product. And so, like, you can take an abstract cohomology in the sense of just a differential complex, not necessarily the exterior derivative, which of course has the graded Leibniz rule and all kinds of neat bells and whistles, right? But you can take an abstract differential complex and build something, maybe not a differential complex, but you can take an abstract cohomology group and build on it something called the cup product and give it a graded ring structure. But the one I'm most interested in, of course, is the Durham cohomology, and here's the graded ring structure on it. Does that make sense why these calculations are necessary?
Mm-hmm.
What are we showing? So if we change alpha by a coboundary, then the wedge product only differs by a coboundary.
Mhm.
And likewise here, if we change beta by a coboundary, the result only differs by a coboundary. So this operation of wedging cohomologous cycles is well defined. All right, moving along. So that brings us to the Mayer-Vietoris sequence. Let me write this down here for you. Did we see this before?
We saw it in homology.
Okay, I couldn't remember.
I think it's how we calculated the homology of spheres.
Oh, okay.
Because you use the fact that I think we use the equator, the fact that that's one dimension lower sphere.
Yeah.
And then we used that with the intersection and showed a bunch of stuff as 0.
Ah. Let's see here. So this should be somewhat familiar then. He calls this M, but M is equal to U union V. And here's his labels: I1, I2, J1, J2. He says this gives rise to the Mayer-Vietoris short exact sequence, which is, I'll show you in a second here. So we've got 0, and then omega of M, where M is U intercept. I'm just going to write it as U union V. And then you got your J star, which takes you to omega u, direct sum, omega v, and then you got your partial I star. I'm not sure if that star is down or up, but anyway, omega
Shouldn't they all be up?
intersect v. Well, good question, Nathan. You're right, they are up. Okay. And then where j upper star of omega, all right, is equal to j1 pullback omega, comma j2, excuse me, j lower 2 pullback omega. Does that make sense? Oh. I mean, J1 is a map from where? From U to U union V. J2 maps from V to U union V. So if omega is a mapping on J is what? I guess for that to make sense, omega should be a one form on the intersection of U and V, right? I mean, if I'm going to take the
Wouldn't it just be like 0 if it weren't? Or wouldn't J's?
Well, I don't understand how I can pull back. Oh, I'm sorry. Pull back. Okay, so it's an omega is a one form, a whatever form on M. And so we're pulling it back to a whatever form on U or a whatever form on V, depending on which we're looking at, the second or the first component there. And that's the direct sum, right? So yeah, so J1 pullback omega is a form on U. J2 pullback is a form on V. That makes sense to be a form. It makes sense to be in the direct sum of forms over U and forms over V, right? That makes sense. Okay. And what's the definition of the other map? All these explicit map definitions, I feel so spoiled. See, here's sorry. Let's see here. Where are we? This guy. So here's what it is. It's the pullback under I2 of beta minus the pullback under I1 of alpha, which he points out is equal to beta restricted to the intersection, right, minus alpha restricted to the intersection. Does that make sense? So we're going from a pair of forms, one on U, one on V, to a form on the intersection. Huh, that's cool. So you just restrict each one of these to the intersection and take their why do we have to take their difference? So that we actually get an exact sequence, right? I guess I could show the sequence as exact here if you want me to. I think I will just read it for you guys though, if you don't mind. He says, I guess I should write, I don't read it, won't make any sense. So first of all, he says if he wants to show the sequence is exact, all right? So if he says J1 I'm not sure what he's defining here. I think he may be defining the symbol I'm writing. I think he's defining this symbol.
Isn't that J star?
Yeah, right. Okay, anyway, the point is, suppose that this is 0, right? Then what? He says that implies that omega restricted to u is 0 and omega restricted to v is 0. Okay, so what are we looking at right now? We're looking at something in the kernel of J star, right? So J star was defined to be this. Right, so when you take the pullback of an inclusion, it's just a restriction. Right? Does that make sense? Like when you pull back a form from U intersect V to U, all you're doing is taking the domain for the form and restricting it.
Right.
So that's what this is. But if you have that omega restricted to U and omega restricted to V are both identically 0, then that implies that omega is equal to 0, where the domain of omega is M, which we define to be U union V, right? In other words, omega is equal to 0 on the union if it's okay, fine. He says, thus, the J star map is 1 to 1, and its exactness at omega M is demonstrated. This is omega M. Right? So could we have exactness of that? He says. Next. What's next? We take eta, an element of omega of the intersection of U and V, right? And he says, take a smooth partition of unity, rho U, rho V, smooth partition of unity, subordinate to the cover U comma V of M, right?
So what does that mean?
Yes. Well, these are two functions that add up to 1 wherever they overlap, if I remember right. So we can
Yeah, I remember we talked about it in Rentland, but didn't define it very well.
Yeah. Just a second here. Give me a second here, I'll give you a full-blown definition. Partition of the unity. Partition, page 30 in here. Alright, a partition of unity on a smooth manifold M is a collection phi sub alpha, alpha and A some index set, of smooth functions on M, such that the values of the functions are between 0 and 1, inclusive, for all alpha, for every map in the partition. The collection of supports is locally finite. That is, at each point P of M, there's a neighborhood W sub P such that WP intersect with the support of phi alpha is non-empty but for all but a finite number. So like basically if you look at M, you pick a point P, right? Then there can be at most like a finite number of these rows, you know. There could be infinitely many such functions.